Okay, welcome back guys. So in this video we're going to cover paper 12 again from May-June 2025, and as always this is 1 hour 45 minutes. So if the video is too slow then I'd recommend watching at 1.5 or 2 times the speed. And of course, as well as watching this video, I will also recommend checking the mark scheme, just to ensure you see the full list of acceptable answers. Okay, question 1 then. A computer stores data temporarily in random access memory or RAM. RAM is one example of primary storage, and we want to give one other example of primary storage. Okay, so primary storage, well, really just RAM and ROM. Of course, you have ROM, well, read-only memory. Alright, ROM is going to be used to store the firmware, things like the BIOS. In contrast, RAM, well, that's going to be used to store the instructions and data that we've currently loaded. Alright, so basically we would have things on secondary storage, so either hard drives, SSDs, but we can't actually access that directly from the processor. First we have to load it into RAM. So also I guess any, for example, user input. Now if the user types something into a field, well again that's going to be stored temporarily in RAM. Alright, now I guess like you can also say for primary storage, I guess cache and registers, although yeah, they tend to be accepted less because I guess they're a bit more niche. They're sort of not really the main ones. Alright, so I guess really just go with RAM and ROM for the primary storage. Right then, B, so give one reason why data is only stored temporarily in RAM. I guess because RAM is volatile, and if we want to store things permanently, well then again we need to save it to secondary storage. For example, SSD, hard drive. So let's just write that. Let's say RAM is volatile. RAM is volatile. Let's say meaning. Meaning once the power is turned off. Once the power is turned off. Let's say what the data will be lost. I think hopefully that should be okay just for 1 mark. If we want to expand that, we could say for permanent storage we would need to use secondary storage. So let's say that maybe for permanence. For permanence, we would need, we would need secondary storage. Alright, and I guess we could give an example, let's say e.g., hard drive, SSD. Then C, the denary numbers 19 and 230 are converted to binary numbers to be stored in the RAM, and we want to convert these two denary numbers to binary numbers. So I guess probably let's just use 1 byte for this. Now if you want, you can write out the positional values, so of course, so if we're using 1 byte, well, we can probably just start on 128, we don't really need to go right to left. So obviously 1 to 8, 64, 32, 16, 8, 4, 2, and 1. So if we think about 19, well of course, 1 to 8, 64, 32, they're too big. So let's just write 3 zeros. Alright, there will be a 16. Right, then there's going to be 3 remaining. So of course, 3 remaining, right, it's not going to be 8, not going to be 4, right, but it will be a 2 and a 1. Then if we say 230, right, this one's a bit more difficult. So right here, there's going to be a 128. Right, there's also going to be a 64. So that's going to get us to 192. There's also going to be a 32. That will get us to, 224. Then there won't be a 16, right, there won't be an 8, and then, we've got 6 remaining. So that should just be 4 and 2. Alright, now I think I'm just going to sort of double check that quickly. I would recommend in the exam, if you have quite a difficult one like this, then it might even be useful to actually write them down and actually do the addition properly. So let's just sort of do that quickly. Right, let's go 4 and 2. So here, 8 plus 4 plus 2, that's going to be 14, 18, and then 20. So let's just carry the 2. Then 2 plus 2 is 4, plus 6, 10, plus 3, that's going to be 30, and then again carry the 1, so 230. Right, hopefully I've not made a mistake there. Then D, the hexadecimal numbers 35, and again, that's hexadecimal, not denary, and AAD are converted to binary numbers to be stored in the RAM. And we want to convert the 2 hexadecimal numbers to binary numbers. Now, if you saw the last video, I mean, this is quite easy. So converting from hexadecimal to binary, again, because we have this relationship, 2 to the power of 4 is 16, then basically 4 bits, or 1 nibble, is going to equal 1 hexadecimal character. So all we have to do, we just have to break these down into the individual hexadecimal digits. Alright, so first we're going to convert 3 into 4 bits. So 3 with 4 bits, well, that's not going to be an 8, it won't be a 4, right, but it will be a 2 and it will be a 1, right, that's going to be the 3. Then if we think about the 5, well, of course, there's no 8, right, there is a 4, yeah, there's not a 2, but there is a 1. Alright, so hopefully that makes sense. Now, again, if you want, you can pause the video, have a go at this one yourself, yeah, if you sort of didn't previously know how to do this. Alright, but here then, well, of course, that's just going to be 8. Right, A, well, that's going to be 10, so 10 is just 8 and 2. Right, and then D, so D, well, okay, right, B is 11, C is 12, D is then 13. So 13, right, that's going to be, well, 8 plus 4, that's going to be 12. And then obviously plus 1, right, that's going to be 13. Then E, the 8-bit binary numbers, right, this and that are stored in RAM. The binary numbers are added together, and we want to add the two binary numbers using binary addition and give your answer in binary, and you must show all your working. Okay, so let's quickly then just recap the rules of binary addition, and I think most people probably know how to do this. So let's say we've got 0 plus 0, and I think here I'm going to write a carry and then also the sum. Okay, so 0 plus 0 has a carry of 0, sum of 0. If we have, well, 1 plus 0, okay, or 0 plus 1, alright, they're both equivalent. Well, here the answer is basically 1, right, obviously, yeah, 1 plus 0 is 1. So what we're saying, the carry is going to be 0, but the sum is going to be 1. Now, if we have 1 plus 1, well, 1 plus 1 is, of course, 2. And if we think, how do we write 2 in binary? Well, we're going to have 1, then a 0. Okay, so yeah, we're going to have a 1 in the carry, just, you know, carrying over to the sort of left position. And then, of course, yeah, sum of 0. Right, then if we get, well, 1 plus 1 plus 1, yeah, that should be a 1 there. Right, okay, so of course 1 plus 1 plus 1, right, that's going to be 3. And the way we represent 3 in binary, well, just 1, 1. Okay, so a carry of 1 and also a sum of 1. Yeah, so hopefully that makes sense. Right, then if we just apply those, so here we've got, well, 1 plus 0, that's going to be 1, 0 plus 0, yeah, that's 0, 1 plus 0, that's 1, 0 plus 0 is 0, right, 0 plus 1 is 1, then 1 plus 1, so here's where we got a sum of 0, but then a carry of 1, right, and then, yeah, this is the one sometimes people get confused about. So 1 plus 1 plus 1, alright, we've got a sum of 1, also a carry of 1, then obviously, well, 1 plus 0 plus 0, alright, that's just going to be a sum of 1. Yeah, hopefully that's correct. Right, then F, it says, an overflow occurs when two other 8-bit binary numbers are added together, and we want to explain why the overflow occurs. Right, and I think here I'm actually going to type because it's a little difficult to actually, yeah, kind of write with this tablet. Right, okay, so overflow, basically we can say this will occur if the answer requires more bits than we have available. And because here, yeah, okay, right, so here it doesn't actually say if we're using 2's complement or not. Right, I guess maybe we can assume we're not because I think, yeah, this one here was not using 2's complement. Right, this 230. Yeah, okay, right, let's, okay, there we go. Right, okay, yeah, so since this 230 was not using 2's complement, then I think maybe they're just talking about the same kind of scenario. Okay, so what we can say is basically the maximum is going to be 255. So let's maybe say, right, when the result, yeah, when the result of the, I guess, right, addition, because that's what they're talking about, let's say requires more bits than are available. Right, and then let's kind of give a specific example. So in this case, yeah, here, right, so in this case, because we've got 8 bits, let's say, right, in this case, if the answer requires more than 8 bits, right, let's say here, right, max value of 255 to be represented. Yeah, okay, I think hopefully that makes sense. Right, then the next one, so the negative denary number minus 22 is stored in RAM. Negative denary numbers can be represented as binary using 2's complement. And we want to give the 2's complement 8-bit binary integer that would be stored for the denary number minus 22. Right, and yeah, we have to show all of our working. Right, so here there's kind of a few ways we can do it. One, we can kind of just do it intuitively, where if we think, yeah, I think I'm just going to write this here. Right, okay, so yeah, okay, the leftmost position or the most significant bit is going to be minus 128. Right, then of course, well, 64, 32, 16, 8, 4, 2, and 1. Yeah, as we've just seen before. Right, so of course, because it's negative, well, this has to be a 1. Right, then we have to think, well, what do we need to add to this in order to get from minus 128, right, back to minus 22? And I think what that's going to be plus 106. Alright, so I think, yeah, minus 128 plus 106 is going to equal minus 22. So in order to make 106, well, that's going to be a 64, right? It's also a 32, that gets us to 96. right, it's not going to be a 16, right, but then it will be an 8, it won't be a 4, and then it will be a 2, right, because 8 plus 2 is going to be the 10. Yeah, that should be okay. Right, now again, yeah, so we can just do it kind of intuitively, basically in our head. The alternate way that often people do is they would actually write this as 22, right, then you would flip the bits and add 1. So let's also try and do that. Yeah, alright, and I think what I'm going to do, maybe let's just do it in a different colour because I don't want to actually write out these positional values again. So let's just do it sort of under here. Right, now if we just want to write out 22, right then of course, well 22 we're not going to have 120, yeah, we're not going to have minus 128. Right, we're not going to have 64, right, we're not going to have 32, there will be a 16, yeah, and there will be a 4, alright, so that's going to give us a 20, right, of course the 2, right, that gives us 22. Right, then we want to flip the bits, so of course flipping these, well 0 becomes 1, yeah, 1 becomes 0, yeah, obviously just, well, sort of go along and flip those. Right, then we just want to add 1, so I'm just going to write out 1 here. Right, that's going to be 1, and then basically we just want to add these two together. Okay, so yeah, that's going to be these two here. Right, so the flipped version, or the 1's complement version, then plussing 1. Right, so here we have 1 plus 1, so that's going to be 0 and carry the 1. Then yeah, 1 plus 0 plus 0, right, that's 1. Right here, well 0 plus 0, that's 0. 1 plus 0, that's 1. 0 plus 0, 0. Alright, then just, well yeah, so 1 plus 0, 1 plus 0, 1 plus 0. Alright, and if we actually look, well here we see, yeah, we've got this answer. Alright, and we actually see, okay, that's going to be the same as this one here. Alright, now, yeah, there are actually, yeah, okay, right, so there's also another way to do it. Alright, and I think maybe I'll just explain this quickly. So if we have the positive number here, and yeah, okay, right, this is kind of a super quick trick that you can use. What you do is you start on the right bit, so you start on the yeah, least significant bit, and again, let's use a different colour here. Right, then what you do is you flip all the bits, right, up to, no, okay, sorry, okay, right, you keep all the bits the same, up to and including the first one that you see. So in effect, right, this 0 is going to stay the same, right, this 1 also stays the same. However, because we've seen a 1 at this point, well, now we're going to flip all the remaining bits. So, okay, this 1 here is going to become 0, right, this 0 becomes a 1, yeah, this one becomes 0, right, that's 1, that's 1, that's 1. Alright, and then again, if we look at this, of course, well, yeah, this purple one, right, is then going to be the same as this orange one. Alright, so there's kind of 3 ways to do it. Although I guess, yeah, the way that they often like is kind of doing this one, right, where you write the positive, right, then you flip the bits, add 1. Yeah, although in theory you can use any of those methods, just as long as you show you're working. Then question 2a, a student has an image file stored in their computer. The image file is taken by a digital camera. And we want to take one box to show whether a digital camera is an example of an input-output process or storage device. Alright, so some people might be thinking storage because of course you can save photos. However, since they only want 1, well of course input is then going to be the most appropriate. Because of course, well, we're taking data from the outside world, right, the physical world, and then we're basically kind of representing that or saving that digitally. Or yeah, we're inputting that into a digital format. Right then, B, so the size of the image file is 3072 bytes. We want to give the size of the image file in kibibytes. Okay, so if we think again, yeah, as we saw in the previous video, then of course, well, kibi, mebi, yeah, gibi, tebi, right, basically you can write that in power, in terms of 1024. Alright, so kibi, yeah, let's write that. Okay, right, so 1024 bytes is going to be equal to 1 kibibyte. Right, then we can just keep going, so we can say, yeah, okay, right, so 1024 kibibytes, right, that's going to be equal to, well, 1 mebibyte, right, 1024 mebibytes is equal to 1 gigabyte, 1024 gigabytes is equal to 1 terabyte. Alright, and yeah, we can also write that in terms of powers of 2, so 1024 is going to be 2 to the power of 10, alright, if we think this one, well, this is actually 1024 squared, because we're saying what that yeah, okay, right. So in terms of bytes, because obviously, well, 1 kibibyte is 1024 bytes, right? Therefore, 1024 kibibytes, well, that's 1024, right? You know, times 1024, right? So that's actually going to be 2 to the power of 20. If we then go gigabytes, right? Gigabytes is going to be 2 to the power of, yeah, 2 to the power of 30. Obviously, tebi, 2 to the power of 40. Right. So what we want to think, yeah, here we've kind of said this. Right, so we say that, yeah, okay, right, so to go from bytes to kibibytes, well, we just multiply by 1024. Alright, yeah, okay, so in order to go the other way, well then we're going to divide by 1024. So if we do 3072, right, divide by 1024, then hopefully we're going to realise, right, that's just going to be 3. Yeah, because if we think, right, it's going to go, what, 1024, well, of course, that's, 1. Right, then if we times that by 2, right, that's going to be 2048. Right, then I guess, well, 3072. And then I think the next one, is it going to be, I think 4096, or I should have remembered that. Alright, and then I guess if we have 8 of them, right, it's going to be 8192. Alright, and these are sort of common numbers that you'll see, when you're working with powers of 2. Right here, then we want to state the number of nibbles in 1 byte, and this one is quite easy. I mean, if we know what a nibble is, right, so a nibble is just 4 bits, right, therefore a byte is 8 bits, well, therefore, of course, 2 nibbles is going to be 1 byte. And we don't really have to show our working probably for this one, although it probably is recommended, actually. So actually, generally, I mean, if it says state, right, generally you don't have to show your working, although if they give you the working space, right, it's probably recommended to do it anyway. Right, then see the image file has a color depth of 32 bits, state what is meant by color depth of 32 bits. So that means that each pixel is going to use 32 bits in order to represent the color. And again, let's just sort of write this because it's going to be neater. So let's say, 32 bits are used to represent the color, let's say what the color value for each pixel. I mean, that should be enough. I think that should be fine. Then if we go to part 2, the color depth of the image is changed to 64 bits, and we want to explain what effect this change will have on the image file. Okay, so the obvious one, well, the image file is going to get twice as big, right? That's in terms of file size. If you want to talk about quality, well, you can say the image will basically be more accurate in terms of the colors represented. Although actually in this case, I mean, if we're using a color depth or bit depth of 32, well, actually, 2 to the power of 32 is equal to, I think, roughly about 4.2 billion. So even with 32, so even with 32 bits, right, per pixel, then we're going to have about 4.2 billion colors. Now, if we make that 64, I mean, 64, well, that's going to give us, some just like gigantic number, which honestly, like, that's going to be more kind of accurate than the human eye can even determine anyway. Honestly, like 32 bits is more than enough. Kind of increasing to 64 won't actually kind of create a noticeable impact, right, for humans. Alright, anyway, let's just sort of try and say what we said about the file size. So let's say, right, since the color depth, let's say since the color depth doubled, the number of bits used to store each pixel, will also double. Let's say hence the overall file size will double. I mean, I think we've said double 3 times, but I guess that kind of makes sense. Right, and I guess that's also just kind of restating the same thing, although they generally do like you to do that for some reason. Right, I guess we can also mention about the quality. I guess we can say also, or I guess maybe as a result. Let's say as a result of more pixels. More colors, or we can say more different colors being available. More different colors being available. Let's say the image will be more accurate, I guess, compared to the original sort of, the original image. If it's a photograph, I guess if it's a purely digital image, right, then there obviously isn't an original. Let's say the image colors will be more accurate, I guess, compared to the original or something. I think that kind of makes sense, right? The image colors, let's say, will be more accurate or will be closer, right, to the original colors. Let's say, if the original was a photo. And I think this, I mean, we don't really need to say, although I think I'm going to say it anyway. Let's say, right, in reality, in reality, a color depth of 32 bits, right, gives, let's say approximately 4.2 billion colors. Let's say what, yeah, hence more is just overkill, or yeah, hence more is maybe not. Yeah, what's a good word for that? I guess maybe not like recognized by the human eye, or not detectable by the human eye. Yeah, okay, right, and yeah, so let's just think, right, the reason I can remember that 2 to the power of 32 is about 4.2 billion, because that's of course also the same as the number of IP version 4 addresses. Alright, so when they say that, yeah, okay, right, yeah, so when they say that we've run out of IPv4 addresses, or, you know, we are running out of IPv4 addresses, again, that's because, well, we have 2 to the power of 32, yeah, because of course, what an IPv4 is using 32 bits. Right, anyway, the next one, so the student uses lossless compression to compress the image file. We want to explain how the image file is compressed using lossless compression. Okay, right, so if they were talking about lossy, well, you can mention what, reducing the resolution, reducing the, well, color depth, bit depth. If they're talking about lossless, then really that's just going to be run length encoding. So let's mention that. Let's say, okay, yeah, and actually sometimes they like to say a compression algorithm. So let's say that, right, a compression algorithm such as, well, okay, yeah, let's write the whole thing, right, run length encoding. Right, then I'm going to say RLE in brackets, just so we can refer to that later. Right, will be used, or I guess, well, could be used. Let's say for RLE, right, just to explain how this works. Alright, basically what's going to happen is we're, well, I guess, well, we, right, the image software, right, it's going to count how many consecutive pixels have the same color, and then rather than storing each pixel individually, instead you're going to store a count of the sort of number of consecutive pixels of that color, right, you know, then the color itself. Yeah, so let's try and say that. So for RLE, right, let's say, yeah, I guess what, a count, right, a count of the number of right, number of pixels of okay, right, let's say the number of consecutive pixels, right, the number of consecutive pixels of that color will be stored, right, let's say followed, yeah, followed by the color value itself. Right, then let's say why this is good. Right, so let's say for an image with many repeating colors. Okay, yeah, alright, okay, let's say what, many repeating consecutive colors. Right, let's say, yeah, this means that we don't have to store as much repeated data. Yeah, we don't have to, right, yeah, we don't have to store the pixel values, or yeah, the pixel values as many times. Right, then let's mention that because we're storing the pixel value and the count, then we can actually just recreate the original perfectly. Right, so let's say, yeah, since we are storing both the pixel value right, and the, I guess what, the consecutive count. Yeah, consecutive count. Right, then we can recreate the original, I guess what, the original image perfectly. Yeah, when it comes to decompression. Yeah, I mean, I think that's really all we can say. I mean, is there any other kind of lossless compression for images? Yeah, okay, right, so I guess there are, but, you know, again, that's going to be beyond the scope for IG. Alright, so I think for IG, it's really just going to be run length encoding. Yeah, otherwise you'd have to be looking at, you know, specific, for example, JPEG compression algorithms, yeah, or, you know, PNG compression algorithms. Right, anyway, then 3. So a program writes a program to store and sort all the data for the books in her home library. The programmer uses a high-level language to write the program. One reason for writing the program using a high-level language is that it's easier to read and write. We want to give 2 other reasons why the programmer chose to use a high-level language. Right, so I guess the first one we can say maybe what, architecture independence, or yeah, architecture / operating system independence. Yeah, okay, all right, let's maybe expand that. Right, let's say processor. So processor architecture, alright, / operating system independence. Right, let's kind of explain what that means. Right, i.e., right, the same code. Right, okay, and yeah, so I guess maybe you can run exactly the same code, because I guess, yeah, different operating systems might have, you know, slightly different features. Yeah, for example, they might have, you know, different file paths, right, things like that. Let's say with no, right, / I guess, well, relatively little. right, relatively little, I guess, modifications, yeah, can be run across different architectures. Yeah, I mean, I think that makes sense. Right, then I guess the second advantage, maybe we can talk about libraries. All right, that most high-level languages, I guess, assuming they're popular, right, usually they're going to have lots of libraries available. Whereas if we think about low-level languages, for example, assembly machine code, right, then of course we don't have many libraries available. Yeah, we actually have to implement that functionality ourselves. Okay, so let's try and write that. Let's say, right, most popular. Right, most popular high-level languages, right, also contain, right, let's say a large amount of built-in, or third-party libraries, right, that we can use, let's say without having to implement the functionality ourselves, right, without let's say having right, to implement, implement or recreate this functionality, right, ourselves. Yeah, that should be fine. Right, so then the next one be the programmer uses an integrated development environment IDE to write the program. One function of the IDE is to provide a translator, and we want to complete the statements about translators. Right, so use the terms from the list. Some terms will not be used, and you should only use the term once. Right, so as I always say with these questions, I mean, generally it's good to actually kind of read these first. Yeah, just read through all the different words. Yeah, okay, where's the pen gone? Right, okay, so I guess, well, the first one, yeah, obviously, well, altogether, all right, just kind of general words. Right, if we think about assembler, so that's going to be the software used to, well, translate or convert, right, so to translate from assembly into machine code. Of course, well, binary, yeah, just base 2 number system, right, error. Right, executable file, well, of course, that's going to be the file that when we double click on it, right, basically it's just going to, well, execute the actual machine code instructions. Yeah, so an executable basically is going to be a list of sort of machine code instructions. Yeah, I guess it can also contain data in the file as well. Obviously, we're executing. All right, if we say interrupt, so that's when the processor is going to be temporarily halted because there's some other event, right? Yeah, some other, well, I guess, interrupt that needs to be handled. Of course, that could be, I don't know, some hardware error. Yeah, it could be a software error. It could be user input. Right, so yeah, user typing, user clicking, right, something like that. Right then, of course, well, line by line, right, partial code, yeah, kind of etc. Right, so here then, a compiler translates the something all at once before something it. Right, okay, so I guess, well, that's going to be whole code. Right, so yeah, the compiler is going to translate the whole code right at once before, and I guess, well, that's going to be executing. Right, so yeah, before running, before executing it. Right, a compiler produces an error report that displays, I guess, yeah, I mean, what all okay, all errors. I mean, that makes sense, right, since it's plural. Right, yeah, all errors. Right, an interpreter translates and executes the code, right, so that's going to be line by line. Right, then an interpreter stops execution when and something is found and continues once it's corrected. Right, so I guess that's going to be error. Right, and I would say, okay, yeah, once you've done these, of course, just read through it again, right, make sure your sort of full paragraph makes sense. Right, so compiler translates the whole code at once before executing it, yeah, that seems to make sense. Right, compiler produces an error report that displays all errors, yeah, it makes sense. Right, an interpreter translates and executes the code line by line. Right, and an interpreter stops execution when an error is found and continues once it's corrected. Yeah, I mean, that makes sense, right? Now, actually, the only thing I would say about this one, yeah, I guess this executing. Now, really, the compiler is not really executing the code. Right, the job of the compiler is actually just to take the source code, right? So to take the high-level language and basically, obviously, translate that into machine code. All right, so let's just sort of draw this. All right, so if we say the compiler, yeah, compiler. So I guess we're in, well, let's say SC, right, the source code, right, obviously coming out, it's going to be the executable. Now, actually, you could create the executable and, of course, not even run that. And that's actually something, that actually happens quite often. For example, maybe you just want to, I don't know, create some final version which, you've already tested, right? You don't actually need to run it again. Alright, so I guess really actually running it, well, of course, yeah, either, let's say as the user, you can, of course, just double click on it, right, if you're using a GUI. If you're of course running it from the command line, well, most programs, I don't know, let's say we have, let's say write p.exe, right, that's the name of our program. So if we just open command prompt and of course type in right p.exe, then if we're in the correct folder, or if we've added that to our environment variables, right, then of course the operating system should find that, should find that executable file, and of course execute that. Right, so yeah, that's okay. Yeah, so that's why this sort of number 2 answer here. I mean, it's not really the compiler that's executing, right? The compiler is just responsible for this, source code into, well, machine code or executable, an executable file. Right, the actual execution, well, again, that's going to be kind of after, right? That's a separate thing. Although if we actually look at the answers here, I mean, none of the others make sense, right? So yeah, I think executing is the only possible answer there. Right, then we want to give 2 other functions commonly found in an IDE, and we want to state the role of each function. Okay, so I'm just going to demonstrate some of these features then in Pseudocode Pro. So I guess, well, first we've got code ed, so right, this is one they often mention. So of course code ed, so well, that's basically just the place where we write the code. Of course, I don't know, just write whatever we want there. Right, then if we look at the next one, context sensitive prompts, right, you can also just call that code suggestions. So for example, if we type in output, or if we type in, what's one of the functions? Let's go, for example, round. Right, then of course it's going to suggest us that function. Right, here is also going to give us a list, let's say the parameters. Right, it's going to give us some help, give us some examples, etc. Right, okay, autocorrection, I mean, I don't really have this. I guess, I'll demonstrate that in IntelliJ. Right, syntax highlighting. So syntax highlighting basically just kind of color coding keywords in different colors. For example, we see here, obviously green, well, these are the modules, right? The built-in functions and procedures. Of course, if we look at blue, well, that's going to be the keywords. I guess white, well, that's going to be the identifiers, right? Orange, obviously the data types. And I guess, this sort of purple, pink, purple, right? That's going to be strings. Right, also pretty printing, auto formatting, and this is something that I think a lot of people would benefit with. Because often, especially when it comes to if statements, when people have nested ifs, right, also loops, people are not using any indentation, and then it actually becomes quite difficult to understand. So here on the site, I do actually have this one, right, this third option. I call it auto format code. You can also call it pretty printing, and if you click this, right, then here we see, just with one click, right, and that's kind of automatically fixed all of our indentation. So generally this does work pretty well. Sometimes it can actually kind of mess up some of the comments, right? But other than the comments, the actual code itself, it does kind of format quite nicely. Right, so code collapsing, basically that's here, so we can just click down on this. So let's imagine we have some, I don't know, massive function, for example, like hundreds or thousands of lines. Of course, we can just temporarily collapse. Collapse or unclapse that. Alright, and then I think actually these were breakpoints, single stepping, and I guess also the autocorrection. Let's just go to IntelliJ here because IntelliJ is going to be more advanced. Alright, now, like if you're familiar, let's say with Python, then of course IntelliJ is just the Java equivalent of PyCharm. They're both made by JetBrains, the same company. Although to be honest, actually IntelliJ is going to have a lot more features than PyCharm, because, basically just because of the sort of language design of Java. For example, things like the fact that you need to actually declare the variable types. You need to declare the parameters to modules, right, functions, procedures. Anyway, so let's just say we make some example. Let's just say string, let's call it A, and let's just assign this 1, 2, 3. Right, now here it's going to give us an error because it said, well, the required type is string, right, but however we've provided an int. Then it's saying, well, either we can wrap using this string.value of, or if we click more actions, let's say we want this one, right, we've made a mistake, and we want to change A to int. Alright, so that one, I guess we can just call it, kind of like auto correction, so error detection, auto correction. Then if we look at breakpoints, so breakpoints, that's going to be a part of the debugger. I guess single stepping, right, also part of the debugger. I guess we can also just add report window. Alright, and again, these three, they're all going to be, I guess, part of the debugging features. Right, so what we can do, and if we see, well, this is just bubble sort. Now, let's say we've actually made an error. For example, this one, right, if we've, say, done less than rather than greater than, because we want to sort of, I don't know, like ascending rather than descending or vice versa. Now, if we actually run this, of course, well, it's just going to execute, right? However, it's going to sort of obviously give us the wrong values and we're not going to know why. So what we can then do, we can just add a breakpoint here, right, just by clicking on the side. Then if we just go, and in fact make sure I use the right one, right, then if we just go debug here, then what this will do, this will open the debugger. One thing it will show us is going to be the report window, and yeah, it does take a little while just to compile it the first time. Okay, right, so since that's loaded, what we can then see, if we look at this one here, right, this is going to be the report window. That's basically just showing us the different variable values at this current time. Alright, and what we can say is actually we've got to this point here, I guess, line 31, and because we've added this breakpoint, well, that just means that code execution is going to pause at this point. Alright, so I guess here, for example, we say times to loop is 8, right, did swap is false, right, obviously inner is 2. Right, then if we click, I think really any of these, I'm just going to click on this one. Okay, so this is going to be the single stepping. And single stepping, this is where we basically execute line by line, right, statement by statement, right. Then we can see how the variables are changing. We can see the sort of outputs, etc. And of course, if we kind of execute line by line, well, then we can kind of pinpoint down the exact kind of cause or the position of the error. Rather than just executing the whole program in one go, right. And that can be quite difficult to determine, what line specifically is causing the error. Whereas of course, if we execute line by line, right, well then of course hopefully we can actually see what line is causing the error. Right, and again that's going to be called single stepping, and if we look here of course we can actually see, so I guess because this is yellow, it's saying it's changed right from false to true. Then of course we can just step through each one. It's just sort of showing us how the variables are changing. Okay, so hopefully that makes sense, what that's doing. And right, if we go here then, and let's just try and explain these. So I think for function 1, I mean, let's just go with something simple. Let's say maybe syntax highlighting. Right, and then so the role, let's say to color code. Let's say different, different keywords. Let's say keyword types, right, identifiers. Let's say data types, right, etc. To make it, easier for the programmer. I guess the programmer to view or understand the code. I guess it kind of also makes it easier for them to spot syntax errors, because for example if they notice that things are color coded wrong, right, maybe that means that they haven't closed a bracket, or maybe that means they haven't, I don't know, closed say a quote, for example, if everything is in the color for a string. Let's say and detect syntax errors. And we can probably say if keywords, or in fact let's say tokens, are the wrong color. Okay, alright, and when we say token, basically a token is just going to be each, let's say keyword, punctuation, right, identifier. Each of those are going to be a different token. Right, then function 2, I mean, let's maybe go for one of the debugging features. So let's say, breakpoints. Right, so the role, let's say part of the debugger. Right, and it's going to be used to, pause. Right, pause execution. Execution of, I won't worry about spelling, right, execution of the program, right, at a specific line. Right, let's say so the programmer, right, can inspect, inspect the variables, right, in the report window. And try to determine, I guess this is going to be quite long, right, try to determine the cause of the error. Okay, right, so I think that's okay. I mean, if we want, we could also mention single stepping, although of course here it does just say 2 other functions. Right, so then see, the program wants to print a list of all her books on paper and identify a suitable type of printer that she could use to print this list. Right, so I think as mentioned in the first video in paper 1, let's just mention it again quickly. Right, now really there's going to be 2 types of printer, I guess for just sort of standard paper. Right, that's going to be inkjet and laser. Now of course you also have 3D printers, but if we're talking about just printing on paper, right, then not really using 3D printers. Alright, so the way that a inkjet printer is going to work is basically it's just going to drop ink, right, so dropping kind of liquid ink. That's my sort of ink bubble. Right, so here then this is going to be the paper. Now the thing is that as this as this ink drops, well, when it lands, it's not going to sort of land and just stay in that position. If you think about water, or I guess any kind of liquid, when it lands, of course, right, that's going to spread out. So we can say actually some of this ink is obviously going to spread in this direction, in this direction. So actually that means that if we want to represent fine details, for example, like small text, then actually inkjet is not that good for representing fine details. The advantage of inkjet is if we want to represent high quality colours, because if we have this liquid ink, well, when these colours are mixed, right, then they can produce, I guess, I know, these vibrant, high quality colours. Right, so if so if here we're just printing a list, right, basically just text, then I think we can just say laser. Right, so yeah, right, a laser printer is going to be better for text, because basically that's just using a powder. Right, and I guess again specifically, well, it's going to be a toner, right? They don't really call it a powder. Right, so yeah, the laser printer is using this toner, and because that's, well, again, it's like a solid, it's like a powder. Right, then it's not going to have this problem of kind of dispersing. It's not going to spread out. Right, therefore, if we want to print text, right, then yeah, obviously a laser is better. If we want to print high quality colours, well, that's when we really want to use an inkjet. Right, okay, the next one, the program needs to connect the printer to her computer. The printer is on the same desk as her computer. We want to give a suitable method of data transmission that could be used to connect the computer to the printer, and we want to explain our choice. Okay, so this one's a bit weird, right? I think there's kind of two different things they're thinking of. Right, the first one was serial or parallel, and then so simplex, half-duplex, or full-duplex. Now, if we're thinking, I mean, all we're doing is just sending simple documents to the computer, so we probably don't really need parallel. I think serial is going to be fast enough, for this particular scenario. Right, now actually, if you look in the mark scheme, you can actually choose any of the options, you just have to justify it. So, okay, so I think for me, I'm going to say that serial was fast enough, because again, we're just sending, sort of simple, like small documents. Right, now you could also say, parallel, and maybe the way you justify parallel is, let's say you're sending, I don't know, some like large PDFs, or you're sending, sort of like hundreds of different documents, like every minute, right? And in that case, if you want something like sort of high speed, many different documents, well, then maybe you'd want parallel. Alright, but I think here, let's just go serial. Right, then we have to think, well, do we want simplex, right, one-way communication? Do we want half-duplex? So that can be, both directions, but not at the same time, okay, only one direction at the same time. Or full-duplex, where that's going to be, obviously, both directions simultaneously. So I think what I'm going to do, I'm going to say serial full-duplex, although again, right, the mark scheme does actually accept any of these. So for example, if you say simplex, you might say, well, maybe we don't need any kind of status messages coming back from the printer. Maybe we only just need to send documents to the printer and that's it. Right, however, I guess in reality, we probably do want some sort of status messages coming back from the printer. Or I guess probably telling us, well, when it's finished, right, telling us if the printer is out of paper, maybe telling us if it's, out of ink, right, etc. Okay, so yeah, let's just try and justify that. In fact, let's just go here, so we get more space. Right, so we can say, right, serial, right, and yeah, this is going to be 6 marks, so maybe we also want to kind of explain what serial is. Right, so serial transmission, serial data transmission, let's say means sending bits one by one, or I guess, sequentially. Let's say sequentially. I don't know what, from the source, from the source to the receiver. Right, let's then say the advantage, because of course, that's what we have to really say. Right, so the advantages, are that it is reliable. Right, it's reliable, simple. Right, let's say it doesn't suffer from skewing. Right, so I think here they say, right, the printer's on the same desk, so we actually don't need long distance communication. Now serial does have the advantage of being good for long distance communication because we don't get this skewing, whereas of course parallel, we do get the skewing, right, therefore it's not good for long distance communication. Alright, now I think I'm not going to explain that because I did explain that in the other video. If you don't know what that is, probably just go online, research, what is skewing, right, parallel data transmission. You should get a nice, simple explanation there. Right, okay, so I guess we can also say cheap. Right, and I guess this is maybe the most important one. Right, let's say and the speed is sufficient. I guess we can say the bandwidth. Yeah, let's say that. Right, and the bandwidth is sufficient. Let's say for I don't know, yeah, home printer usage. Right, let's say i.e. right, sending small number or small numbers of relatively small documents. Yeah, that makes sense. Right now, if for example, again, yeah, okay, so if you're working in some kind of like industrial print shop that's having like thousands of people sending, obviously like thousands of documents every minute, well, maybe then you would want parallel, of course, for that increased speed. But yeah, I think here, just for again like a sort of home use, right, that's not really required. Right then, if we say full duplex, again, let's just sort of explain what this is. Right, so full duplex means what data. So yeah, data can be sent in both directions simultaneously. Right, okay, yeah. So when we say both directions, let's say from the computer to the printer and vice versa. Right, from the computer to the printer. Right, yeah, and vice versa. Right, okay. Right, and then let's say simultaneously. Right, let's say, yeah, this is advantageous, or yeah, this is maybe a benefit. Right, advantageous because, and again, let's try to think of a specific example. Let's say what the computer could be sending a new document to be printed, right, as the printer is telling us that the current document has finished, or the printer is out of paper, out of ink. Yeah, let's say that maybe because, right, okay, let's say events. Right, events could occur on both the computer, right, computer and printer. I guess simultaneously or at the same time. Let's say you're e.g. The computer sending more documents, to the printer. Right, let's say and the printer. Right, simultaneously. Right, let's say sending a message, or sending messages, right, back to the computer. And again, let's give an example here. Right, let's go e.g. I know what sort of print job finished. Yeah, I guess what sort of print job successfully finished. Maybe let's say error. Yeah, let's say error codes, or I guess errors. Right, yeah, errors such as right, printer, out of paper. Right, I guess out of paper ink. Right, something like that. I guess toner. Yeah, so I think hopefully that's going to be enough there for 6 marks. Right, okay, then I guess actually another sort of long written question. Right, so an even parity check is used to detect errors in the data after it's been transmitted to the printer. Describe how an even parity check detects an error. Right, so let's just sort of quickly go over parity again. I mean, I think most people are probably sort of familiar, right? They should remember this. Right, so basically then we're going to break the data down into bytes. I guess really just into 7 bits, right? And then of course we add the parity bit at the front or at the end. Yeah, both are okay. Alright, so let's say we have some, I know some like 7 bits like this. Okay, right, and what we would then do, because we want even parity, well, we then just count how many ones there are. Of course, here there's 3. Right, then we're just going to add, and let's just do this in a different colour. Right, okay, yeah, so then we're just going to add the parity bit. And what we want to do, well, we want to add a 1 so that the total number of ones becomes even. Right, so of course here we're going to add a 1, right, and then in total that's going to give us 4 ones. Of course, if we were using odd parity, well, then we would add a 0 in order to keep this as being an odd number of ones. Yeah, however, since here they've said we're using even, yeah, then that's kind of what we want to explain. Yeah, so let's just try to explain this. So let's say, okay, so I think always you want to talk about the sender and receiver, right? So the sender will break the data into, I guess, 7-bit chunks. Yeah, I guess, ready for the parity bit to be added. To make it 8 bits in total, or I guess 1 byte in total. Right, okay, let's say yeah the sender. Let's just repeat ourselves there. Right, okay, the sender will then count the number of ones in each of these 7-bit groups. Right, each of these 7-bit groups. And I guess determine if there is, or I guess is an even or odd number of ones. Right here, let's say if there's if there's already an even number of ones, right, then a zero will be added as the parity bit. Else a 1 will be added as the parity bit. I think that's fine for the sender, right? Then we can say what the sender will then send the data. Let's say that the data is then sent. So like maybe they'd want us to say the data including parity bits, although we've kind of implied that already. So the data including all parity bits is then sent to the printer. Which will then check. To ensure that each byte also contains an even number of ones. Let's say so if it does, then the printer assumes the byte has not been corrupted. The byte is not. The byte is not corrupted. Let's say else. Else if there's an odd number of ones. Then the data is assumed to be corrupted. And I guess can be handled. Let's say appropriately. And let's give an example, so e.g. Being asked to be resent. And again, for 4 marks, I think that should be enough there. Then number 4, an employee uses a computer as a von Neumann architecture to complete many different tasks in their working day. The computer has a central processing unit or CPU, and we want to complete the table of components in the CPU and their descriptions. So of course components, physical components, hardware. So description, it sends a signal to all the components in the CPU to manage the flow of data through the CPU. So if this is talking about, just sort of managing the CPU, then hopefully we know that's going to be the control unit. And I think, again, we did talk about the control unit quite a lot if you've seen, paper 11, the first video I made. The control unit is going to be responsible for a lot of different things. One is going to contain the system clock, which of course is used to synchronize the components. And of course on each clock tick, then that's going to be a new fetch, decode, execute cycle that starts. It's also going to be, and actually this is really the main purpose. The control unit is going to be responsible for decoding the instructions. Again, I sort of explained what decoding means in the previous video. Basically it means taking the actual bits and then working out, what's the opcode, what's the actual instruction? Is it add, is it load, is it store, is it, multiply, shift? Then also kind of figuring out, what's the actual data, what's the opcode? And I think I don't really have time to explain that again because, otherwise the video will be 2 hours again. And I guess also the control unit, so I guess here where it's just going to, obviously send signals to the components, basically telling them what to do. So if, for example, we have an add instruction, then it's going to send a signal to the ALU, because the ALU is going to be the component that's responsible for performing that add instruction. If, for example, it's a load instruction, then the control unit will send a signal, let's say to the memory components, So that could be cache, it could be, it could be RAM, it could be, even like secondary storage. Although really those signals will just be sent on the various buses, the address bus, the control bus. And I guess if you're writing, then there's also data that's being sent out from the CPU, on the data bus as well. Alright, anyway, so the next one, so here then it carries out all the arithmetic and logic operations in the CPU. So I think here they kind of give you this almost, right, that's going to be the the ALU, right, so the arithmetic, let's say what arithmetic and logic unit. Yeah, and I guess you could just say, right, ALU, just put that in brackets if you want. Right, then if we say cache, so yeah, let's maybe just type this. Right, so cache basically is going to be, I guess so fast access and I guess small. Right, so yeah, small fast access memory inside or shared between the cores, and it's going to store the commonly used or prefetch instructions or data, or yeah, I guess and data. Right, so let's try and explain, or let's try and write all of that. Let's say small, small temporary, and fast access memory. Right, let's say we're in, I guess we're in, right, or shared, shared between the different cores. Right, so it's going to stores, let's say commonly used, right, slash prefetched. Okay, how to spell fetch, I guess like that. Right, okay, so yeah, prefetched instructions, right, and data. Alright, now again, I did kind of explain this in the other video. When we say prefetch, what this means, and I think I'll use the taxi example. Now, okay, right. So let's say we need an instruction. Now we don't want to load the instruction kind of like immediately when we need it, right? Because actually that takes time, right, loading it from RAM. So what we can actually do is we can load, let's say, the next 1,000 instructions in advance. So if we think again about the taxi example, now if you're in a hotel and I don't know, you want to get a taxi to the airport, now of course you could walk outside, right, walk down to the hotel entrance, and then of course, just like call a taxi. But if you do that, you're probably going to have to wait, 5, 10, 20 minutes for the taxi to arrive. Now, if in contrast you're in the hotel room and you think, well, I'm going to need a taxi in, 10 minutes, right? If you then call the taxi when you're still in the hotel, right, then obviously by the time you walk downstairs, well, at that point the taxi should hopefully be there waiting for you. So that's kind of what we mean by prefetching, where we're basically loading the instructions in advance of when we need them. So hopefully that kind of makes sense. Alright, then if we say the program counter, so this is going to store the address of the next instruction to be fetched, or the next instruction to be executed. Let's say that stores the memory address. The memory address, right, of the next instruction, I guess, to be, fetched, right, decoded, executed. Obviously just, part of the fetch, decode, execute cycle. Right then, okay, where's the mouse? There we go. Right, so here then it's going to control the number of fetch, decode, execute cycles that are performed per second. Right, so that's going to be the system clock. I think just saying the clock is going to be fine, but okay, let's just go system clock. Right, okay, then the last one, so it stores data immediately before it's transmitted to RAM and immediately after it's received from RAM. Okay, so this one is possibly a bit more difficult. Let's just I think here we can draw it. Right, okay, so what we're going to have, and let's just try and draw this quickly. Right, okay, so here then this is going to be the CPU. Of course we have all the different registers, right, like the PC, MAR, MDR, right, CIR. Obviously things like the ALU, the control unit, right, status register, index register. Alright, I think the one, the one we're talking about here is going to be the MDR. Right, the memory data register. So let's say we have some data that we want to write, and right here let's just do RAM. And I think also let's just go MAR as well, because we will also need that. Alright, and let's say here this is the control unit, and then I guess we've also got the ALU. Okay, so let's say we've done some calculation, and I don't know, let's say the ALU equals like 99. Right, then what's going to happen is if we want to write this to memory, well, first this 99 is going to go into the MDR. Let's draw that here. That's maybe not a good diagram. Right, okay, because of course all of this is inside the CPU. Right, okay, so let's say the memory data register is now going to contain the data 99. Right, let's say we want to write this to memory address 10. Well, then we're going to put 10 in the MAR. Right, now what's going to happen is because we want to write, well, the control unit is then going to send a write signal. So here we're going to have the 3 buses. Okay, right, so the read-write signals, that's going to be on the address bus. Right, obviously, while the memory data register, of course, well, that's connected to the data bus. And then obviously the memory address register. Okay, sorry, hang on. Yeah, I think I said that wrong. Okay, sorry, right. So the read-write signal, right, that's going to be sent on the control bus. The memory data register, of course, well, that's connected to the data bus. Obviously, memory address register, right, that's obviously connected to the address bus. Right, so basically what's going to happen, and let's say again that maybe a read has a value of 0, right, and write means 1. So if we want to send a write signal, well then we're going to send 1 on the control bus. Right, obviously the data we're sending on the data bus is going to be 99, right, and the address, well, we're sending 10. Right, so when these 3 bits of information arrive at the RAM, well then what RAM can do is, of course, it can think, well, 99 is the data, right, obviously the address that we're sort of looking at is going to be 10, right, and the operation to perform is going to be read, right. So when it has those 3 bits of information, right, then of course it can go to memory address 10 in RAM, and of course just write that there. Now if we think about, let's say if we want to do a read, right, so just doing the opposite, and let's say here, I don't know, we have like 123, and let's say that's in let's say address number 100. So what we would then do if we want to read from address 100, and let's just try to how to get rid of that. Okay, right, there we go. Right, let's just erase this just so we can sort of see it again. Okay, right, so if we want to read, now what we would then do is we would say the address we're reading from is going to be 100, right? So here then we would send 100 on the address bus. Right, here on the control bus, then we need to send the signal. So let's say 0, right, so 0 means that we want to read. Of course, right, when this 100 and 0 arrives in RAM, right, and okay, notice here we don't have to send anything on the data bus since we're not writing any data. Okay, right, so when this 100 and 0 arrives in the RAM, well then of course RAM is going to check address 100, right, it's going to see what there's 123, right, then it's going to take this 123, and of course it's then going to send it back on the back on the data bus. And that's also why we think then that if we think the data bus, well, that's going to be bi-directional, because of course we need to send data both ways. Likewise the control bus, right, again that's bi-directional. For example, we're sending, I know, read signals, write signals from the control unit, right, things like clock, right, system clocks, timing pulses, right. However, we're also sending things back, for example interrupts, right, error codes, various things like that from the hardware components. However, the address, well, this only has to be one directional, I guess, well, unidirectional, because we're saying, well, yeah, this is the address, let's say, to read from, right, but actually we don't need to send an address back to the CPU, okay, because of course, well, the CPU doesn't actually have any addresses. Alright, so yeah, hopefully that makes sense. Alright, so then if we just read this again, it stores the data immediately before it's transmitted to RAM and immediately after it's received from RAM. So if we go back to our diagram here, well, that's going to be this one, right, the NDR. So I guess here you probably want to write that in full. Right, so well, memory data register. And then again, obviously in brackets you can put MDR. Right, okay, then B, so the computer is an example of a general purpose computer and not an embedded system. Explain why the computer is not an embedded system. Okay, so yeah, I was going to say, well, obviously a computer is general purpose, however, they've kind of said that already. So I guess a computer can be used for many different tasks, while an embedded system is, well, just designed for, one or a small number of tasks. So let's say, let's say the computer, can be programmed, or used for many different tasks. While the embedded system, maybe comes like pre-programmed, with, I guess, specific functionality, limited, limited functionality, that can't be easily changed. Alright, so for example, let's say you have, I don't know, some digital watch, or some smartwatch. Well, it's probably going to be difficult to, let's say, change that digital watch, right, into, I don't know, some, like games console, for example. Because, yeah, you don't have the hardware, obviously the sort of code has been pre-programmed in already. I think that's okay, right? I mean, we can probably also mention about the hardware as well. So let's say maybe, Alright, and again, I don't really want to say like general purpose, because they kind of have said that. I guess maybe we can talk about powerful. Right, so let's say the computer, right, will, I guess, yeah, maybe let's say likely, right, maybe have more, I guess well, yeah, more powerful hardware. Yeah, alright, and is there another word for general purpose? So maybe more powerful hardware. And again, I guess that can be used for many different tasks, although that's kind of saying what we've said already. Yeah, many different tasks. Let's say, yeah, while. Right, and yeah, okay, I guess here we could mention a specific example. Right, so if we're talking about specific hardware, let's say, I don't know, your e.g., right, CPU, right, graphics card. Right, let's say, yeah, while the embedded system, yeah, let's say what will likely have, I guess, what cheaper, I don't know, yeah, cheaper, less powerful, kind of more specialist, or just, you know, sort of more designed just for one purpose kind of hardware. Yeah, let's say we'll likely have maybe more specific, right, and possibly, right, cheaper / less powerful hardware. Yeah, I think that should be fine. Right, then I think this is the last question. So a hospital has computers and technology that it uses when caring for its patients. Right, one computer is an expert system that is used to help diagnose the patient's illness. The doctor inputs the patient's symptoms into an interface and a diagnosis is output. And we need to describe how the expert system decides on the diagnosis. So I'm going to try just to explain this with this screenshot from the book. Yeah, this is the Cambridge book, right? It's quite a good diagram they have here. Right, so just explain how an expert system works. Well, of course, right, first you've got the user interface, and that's going to act as both an input and output for the user. I guess here they're sort of showing them speaking, but of course it could be typing, it could be clicking, yeah, it could be a, you know, touch screen, or it could be movement, it could be anything. Right, I guess what they say, this is then connected to the explanation system and the inference engine. Basically, that's the actual software, right? That's the actual expert system code. Yeah, and I guess really right, first we really have to think about the knowledge base and rules base. Right, so the knowledge base, this is just going to be a list of all the facts that are known. So I think the example they use in the book is basically different animals, or sort of categorizing different animals. So for example, you can just have yeah, kind of like a list of knowledge. So let's say we have a dog. Now maybe a dog, right, that's going to be a mammal. It's going to have 4 legs, right? It's going to have fur. Yeah, it's going to be I don't know, you know, sort of warm-blooded, right? You know, all these different properties, right? So all of these properties about the different animals, right, or in this case the different diseases, are going to be in the knowledge base, right? Then we get yeah, okay, right, and I guess really the knowledge base, I mean, you can think of it just like a big spreadsheet, right? Just a big table. Right, okay, then the rules base, these are basically just going to be a load of if statements. In reality, I guess you'd call it a decision tree. So let's say, for example, can I, yeah, okay, can I sort of go down on this? Right, okay, so let's say, for example, we have our first decision, and let's say that can be like mammal. So yeah, we're just going to ask, right, is it a mammal? And let's say if it is a mammal, well then maybe we want to ask, I don't know, you know, can it swim? Alright, and let's see if it can swim, well then we say, I don't know, you know, sort of does it live in water, or, you know, does it live on land? Right, so basically we're going to keep asking these questions, and then, you know, eventually, well, we then should get, I don't know, you know, like dolphin, for example. Alright, so if we just keep asking these questions, right, more and more, then yeah, we should actually get to the kind of leaf nodes, right, we should get to the end. Alright, and I guess like an equivalent question, I don't know, like here we can ask, you know, can it fly, for example. Of course, yeah, just keep asking these questions. Alright, so hopefully that makes sense what the rule space is, right? Basically just this sort of list of if statements, really. Yeah, this decision tree. Alright, so the inference engine, what that's going to do, the inference engine is going to use the rule space, okay, obviously, yeah, this list of if statements, right, combined with the knowledge base in order to kind of determine, right, what the result is. So to determine, right, this disease is, I don't know, you know, cancer, or yeah, this disease is Alzheimer's. Right, then the explanation system, that's basically going to take the inference engine and it's going to say kind of why we've arrived at this result. So for example, if we say here, and to be honest, like, I'm not sure if this is correct, I mean, like a dolphin, right, maybe it's a mammal, maybe it's not. Yeah, my, you know, biology knowledge is not too good. Right, but let's say here, okay, right, if we sort of get the final answer of dolphin, right, we can then basically just kind of backtrack up this decision tree, and we can say, well, the reason we think it's a dolphin is because, you know, I don't know, it has like smooth skin, right, it can swim, and it's a mammal, for example, right? So we can sort of go back and obviously tell them why we think we've arrived at this answer. And we can also give a percentage. So we can say, well, we believe there's like an 80% chance it's a dolphin. Yeah, now, to be honest, I guess if you have a simple decision tree, I mean, maybe you wouldn't necessarily have percentages. But I guess, yeah, other systems, right, they can give a percentage like that. Yeah, if it's not, you know, like 100% certain. So yeah, I guess we really just want to try to explain all of that. So right, they're talking about diagnosing the patient's illness, and yeah, actually this is kind of annoying because you can't. It kind of blocks out the text. Right, so the doctor inputs the patient's symptoms into an interface. Describe how the expert system decides the diagnosis. Okay, so let's say maybe these symptoms. Right, these symptoms. Right, input. Maybe what will be, let's say, will be used. Right, yeah, will be. Okay, alright, okay, yeah. Let's say input right into the interface. Yeah, let's try and get all of these keywords. Right, so the symptoms input into the interface will be used, right, by the inference engine. Let's say to, I guess maybe determine what rules are matched. Let's maybe say that, right, to determine what rules, right, are matched, right, in the rules base. Right, and then I guess we can sort of say how we determine, you know, if a rule is true or false. Right, let's say, yeah, the way the rule, right, is, I guess, I don't know, yeah, considered to be true or false. Right, yeah, okay, right, so I guess we can say evaluated. Right, the way the rule is evaluated, right, is by comparing what the user input, right, with the known, let's say, okay, with the known knowledge, right, with the known knowledge, I don't know, maybe previously entered by a human expert, right, by a human expert, right, into the expert systems, or, well, yeah, okay, right, I guess just into the knowledge base. Yeah, into the knowledge base. Yeah, I think that's fine, right, then maybe we can give some examples. So, for example, right, if they enter, right, I know, yeah, if they enter symptoms, right, of, I know, let's say fever, right, then certain diseases, right, in the knowledge base, yeah, I guess, I don't know, yeah, will be matched. Right, okay, then we can say what the more symptoms they enter, the more we can kind of like focus down on what disease we think it is. Right, the more symptoms, right, the more symptoms that are entered, right, the more, I don't know, yeah, the more we can focus. Okay, right, yeah, okay, right, let's mention in terms of the rule space. Right, let's say the more, the more rules, I know, yeah, the more rules in the rule space will be matched. Right, in the rule space will be matched. Right, hence a more accurate, a more accurate diagnosis, right, is likely to be, achieved. Yeah, that's fine. I mean, we could mention the explanation system. Let's just say that quickly, right? So the explanation system is used to inform, I guess, inform the doctor. Right, inform the doctor, right, as, well, yeah, I guess just why. Let's say, right, why this particular diagnosis, right, diagnosis has been reached. Well, yeah, I think that's fine. Right, has been reached. Yeah, so hopefully that should be enough to get 3 marks. Right, then the next one, the hospital has a robot that's used to perform surgery. A doctor controls the robot from a different location to perform the surgery on a patient. One feature of the robot is that it has electrical components. We want to give examples of the electrical components of a robot. Okay, so I guess we can say CPU or processor. Let's just say that, right? Let's say CPU. Yeah, okay, right. I guess here sometimes they call it microprocessor. Yeah, although to be honest, if it's like quite a complex robot, then you also need quite a powerful CPU. Right, I mean, other ones, I guess what you can say sensors, you can say memory, you can say actuators. Yeah, I think any of those would be okay. Let's say maybe sensors, right? Because yeah, I guess most robots are going to have sensors, right, to sort of detect their surroundings, right, things like that. Right, then we want to explain the advantages of using the robot to perform the surgery. Okay, so let's just go back. Yeah, let's see if there's any specific details. Right, hospital has a robot that's used to perform surgery. Doctor controls the robot from a different location. Right, so of course, yeah, that's going to be one of the advantages that we have to mention. Right, let's say that. Yeah, the surgery can be performed remotely. Right, e.g., yeah, if the doctor is on holiday. Yeah, or okay, yeah, all right. Let's say yeah, or if there's not a doctor with this specialist skill right in this location, because maybe they have some super rare disease that only 10 doctors in the world are able to treat. While realistically, like maybe they don't have enough money to fly to that other country, right? Yeah, and I guess likewise the doctor is not going to be able to fly to them. Right, so I think we can sort of mention that. So yeah, if the doctor is on holiday, right, or yeah, maybe if it's a rare disease. Yeah, if it's a rare disease, slash, yeah, I know, yeah, not many doctors can treat it. Right then, yeah, what then? This allows the patient to be treated. Yeah, I know, yeah, from, I guess, well, yeah, by a doctor. Let's say regardless of where they are in the world. Yeah, I mean, I think that's okay right then for 4 marks. So, like, maybe you can think that the robot might be more accurate. I mean, I guess, humans, right, if you're sort of thinking about surgery, I mean, honestly, like, your hand is, not going to be completely steady, right? You're going to be shaking. Yeah, obviously, even like a professional doctor, they're not going to be completely still. Yeah, that's just sort of human. So I guess maybe we can mention that. Let's say, right, a robot, right, might also be more precise. Right, let's say, yeah, e.g., won't be shaking as much. Yeah, maybe can, I don't know, yeah, can perform smaller cuts or something. Yeah, maybe can perform, right, more accurate, right, or smaller, yeah, smaller cuts. Yeah, maybe is more repeatable, right? It can sort of do the same thing over and over again. Whereas I guess a sort of real human, right, you're going to be slightly different each time. Yeah, maybe has right, has more consistent behavior. Right, more consistent, yeah, behavior, right, etc. Yeah, I don't know. Like, is there anything else you could? Yeah, okay, right. So I'm thinking about the price. I mean, like, you're not really going to be saving money because of course you also have to pay for the doctor as well. So in reality, you're paying for the doctor and the robot, which is probably going to be more expensive than just having the doctor there in person. I mean, I don't know, like, possibly you can mention something about hygiene. You can say, like, maybe the robot is cleaner, rather than having like an actual doctor, because of course, while the doctor, they're going to be breathing, even with a mask and stuff. Yeah, I don't know. So like maybe that could be something you could write. Let's say, yeah, maybe the robot, right, might also be more hygienic. Hygienic slash, right, sterilized. Yeah, than having, I don't know, sort of humans. Yeah, than having humans in the room or having the doctor in the room. Yeah, that's probably not a very good example, but yeah, okay, right. To be honest, this question is a bit difficult because if you actually look at the mark scheme, right, they do actually require quite a lot of kind of biological knowledge. So yeah, I guess if people are doing biology, or if, for example, they have doctors in their family, right, then this is probably quite easy. Yeah, if you don't, right, then maybe you're going to be kind of struggling for what to write on this. Right, anyway, so then we want to explain one disadvantage of using the robot to perform surgery. So I guess the disadvantage, well, if it breaks, then yeah, they may not have anyone there to fix it. Like you can probably also mention maybe the robot is going to be more difficult to control, because I guess humans are quite tactile. You know, obviously we can like move our hands in like every different direction. Yeah, obviously, you know, we have our fingers to sort of move easily. Yeah, whereas maybe the robot is not going to be able to move as freely as a human. Alright, I think I'm probably going to go with the if it breaks. So yeah, let's say if the robot breaks. Yeah, well, okay, let's say if it breaks slash, maybe, I don't know, like encounters problems. Right, let's say, yeah, then, right, then if, right, if there, yeah, okay, right, let's say, yeah, if there is no one there, with the required skills, right, requires skills, well, or knowledge, right, knowledge to treat the patient. I guess what, yeah, then it can endanger the patient, or it could become a dangerous situation. Right, let's say that, yeah, the situation could become dangerous. Yeah, dangerous for the patient. Yeah, okay, I think that's probably okay. Right, we could say what the robot might not be able to be repaired in time, you know, during the surgery. Yeah, let's say that, right, the robot may not be able to be repaired. I don't know, yeah, sort of like during the surgery. I guess, yeah, particularly in like time critical situations. Yeah, particularly for, I don't know, yeah, time critical treatment. Yeah, that should be okay. Right, then I think, okay, right, no, it's not the last one. Right, so then patients use the web page to log into their account to pay for the treatment they've received in the hospital. The patient enters the uniform resource locator URL for the web page into their browser, and the web page is requested and displayed. Complete and annotate the diagram to show how the web page is requested for the patient. Okay, right, so URL is input into the patient's computer. Right, so here then I guess they want us to talk about DNS. Yeah, so let's just try and draw this. Okay, so I guess, I mean, we could sort of mention that this is the web browser, because, yeah, I guess you're going to have the web browser, yeah, obviously, like, in the computer. Right, so what this is going to do, and I guess we could also mention that first the DNS request is, okay, yeah, sorry. Right, so first the DNS record is going to be checked to see if it's in the web browser. So let's say obviously they're going to this website here. Now, basically the web browser will check, right, does it know the IP address for this particular website? Right, because of course, let's say for humans it's easy to remember domain names, it's easy to remember URLs. Right, however, for computers, when you're talking about packet switching, or well, yeah, network devices, you know, routers, etc., right, they're not actually going to use the domain name, right? They're not using the URL. They're just using the IP address in order to send packets over the network. Right, that's why we need the DNS domain name system in order to convert from the domain name, right? So the kind of, you know, text, yeah, this textual domain name, right, into the IP address. So let's say that, maybe let's go one, and I probably should have given more space here. Right, so one, let's say web browser, right, checks, I know, yeah, to see, right, if it knows, yeah, to see if it knows IP, yeah, I guess what IP address, right, of website. Yeah, all right, and I guess it's kind of two, right? So web browser and the OS, right? So yeah, both of those are checked. Right, if not, well then it's going to be sent to the router. Right, let's sort of do that there. Right, let's go router. And to be honest, yeah, this is going to be quite repetitive. Yeah, I know, right, checks. I know, yeah, like checks for IP. Yeah, checks for IP address. Right, okay, then if that's not known, well then from the router, right, then it's going to go to the DNS server. Right, and actually there's kind of multiple of these. One, the ISP, right, the internet service provider is going to have a DNS server. Then there's also global DNS servers if those don't know. Yeah, I guess we don't really have to do that much detail. Right, let's just say, well, DNS server. Right, checks for IP address. Right, okay, then this will then be sent back. Okay, so yeah, and this is kind of quite messy, right? So let's say DNS request. Alright, so the DNS request will go to the router. Of course, if the router doesn't know the IP address, well, then that will send it to the DNS server. Right, then what's coming back? That's going to be the IP address. Right, yeah, the IP address. Okay, so then what can happen? Well, then we're going to have the web server down here. Right, let's go web server. And I guess we can say, in particular, it's the CI hospital. So let's go, yeah, CI hospital web server. Or, well, yeah, cihospital.com web server. Right, so then what's going to happen is here then we're going to send an HTTP request. Yeah, I guess we could say, you know, HTTPS request. Right, let's get HTTPS request. Let's say sent. I know, yeah, sent to hospital's web server. Or well, sent to hospital's IP, or yeah, the IP address. Right, okay, and then yeah, when the web server then receives that, well, this then is when it can send the content back. So I know, let's say, well, I guess you get HTTP, yeah, HTTP or S, let's say response. Right, and then some of the things that could be sent back, well, that can be HTML, right, the hypertext markup language. That can also be, for example, CSS, right, cascading style, yeah, cascading style sheets. Basically the appearance of the website, right, the different colors, yeah, the sizes, the fonts, right, things like that. I guess we'll also like JavaScript. Right, I guess things like, well, sort of, okay, yeah, let's just say media. Alright, because I guess media is going to cover everything, right, so images, audio, video. I mean, yeah, not really sort of Flash or anything, yeah, not really anymore. Alright, so yeah, hopefully that makes sense, right, and I'll try just to explain it once again. Let's just use different color here, maybe green. Right, okay, so first thing what's going to happen, we basically need to convert this domain name into the IP address. Now, it's going to be a hierarchical process. So first, the web browser is going to check, does it know the IP address, right? If it doesn't, well, then we're going to check in the operating system, does that know the IP address, right? If it doesn't, well, then it's going to be sent to the router, yeah, obviously the DNS request. Right, again, if the router doesn't know, well, then obviously it's going to be sent to, well, the sort of ISP's DNS server. Right, obviously, if that doesn't know, well, the global DNS servers. Right, eventually someone, or yeah, one of these devices will know the IP address. Right, this is then going to be sent back, and we could actually mention, let's say maybe IP address, right, okay, yeah, that's going to be cached. So basically this IP address will be saved in the router, so that if, let's say, in 5 minutes we also go to this website again, well, then we don't also have to go to, you know, the global DNS server again, right? Instead, we only have to go to the router, yeah, because the router has temporarily saved the IP address, yeah, for this website. Okay, right, so once we've received that then, yeah, once we've got back here and we've received the IP address, well, now we actually know the IP of, well, yeah, of this, you know, website we're trying to visit. So then we can send the HTTP, or well, HTTPS, right, obviously the S meaning secure, yeah, hypertext transfer protocol. Right, this request then goes to the IP of the yeah, of the web server. Right, the web server is then going to process that request. So we could say that, right, web server, yeah, maybe I know processes request. Right, and then obviously with that, yeah, with that processing, well, then it's going to generate the things to send back. So that's going to be the HTTP or HTTPS response. And again, the different things, well, it can be the HTML, right, so the page content, yeah, the CSS, right, the page appearance. JavaScript, so the page functionality, right, when you click a button, right, things like that, what happens, and obviously again, right, the media, the images, the video, the audio, yeah, etc. Okay, and then I think, yeah, this is the last question, right, quite a difficult one to end. So a patient is making a payment through a secure connection. The secure connection is created using the secure socket layer, right, SSL protocol. We want to explain how a secure connection is created using the SSL protocol. So I think for difficult questions like this, it can actually help to write down, well, either a simple plan or at least some of the keywords you want to talk about. So I think probably something we want to mention, well, it's going to be the client, I guess, well, obviously client and server. We also want to talk about, well, digital certificate. We also want to mention the certificate authority. I guess we also want to mention digital signatures. Yeah, we could mention, I guess maybe like encryption. Yeah, I guess, well, like asymmetric encryption. And then we could mention, for example, part of the certificate, well, there's also going to be the public key. Yeah, I guess also, well, the private key as well. Yeah, although of course, okay, yeah, so right, the public key is sent with the digital certificate. Of course, the private key, well, that's always kept private by the server. Yeah, I think that should be enough probably that we can talk about. Right, so let's just sort of try and start typing here. Right, let's say the client, right, so probably we want to say the client will request the digital certificate. Right, request the digital certificate from the server. Right, let's say, yeah, this certificate, well, this digital certificate. Right, this certificate, will, yeah, okay, I'm not going to worry about the spelling. Right, will contain, let's say, information, right, such as, right, the server's public key. Right, and okay, yeah, that's going to be used for, let's say, right, used by the client to, to encrypt, to encrypt messages to the server. Yeah, all right, and yeah, okay. I guess we could mention specifically that's going to be asymmetric encryption. Let's probably say that. So, okay, here we go. Right, so used by the client, let's say in asymmetric encryption. Yeah, okay, to encrypt messages to the server. Right, there's also going to be the digital signature. Right, digital signature signed by the certificate authority. Okay, and when we say certificate authority, basically that's going to be a reputable organisation, and in theory what they should do is they should actually validate the person who owns, or I guess, well, verify the person who claims they own this server. So in theory, you know, when you actually buy a web server, right, in theory, well, you have to provide your email address. I mean, if you're a company, then you can also provide additional details. For example, maybe a telephone number, maybe a physical address, right, things like this. Now, the certificate authority is supposed to actually verify that information. Again, if you're just an individual person, I mean, you don't really have to do that. However, if you're a company and you want, I guess, kind of the extra reputation, right, then yeah, some companies will actually pay for this verification process, just so it means that then people that are using the website, in theory, will actually be able to trust them more, right, since they've been verified by this third party. Although, to be honest, you know, most people are not actually checking the digital certificates, right? They're just going to a website, and yeah, they're just kind of assuming that it's valid, right? Assuming it's the person they say they are. Right, so yeah, we can say, right, digital signature signed by the certificate authority, right, to, I don't know, yeah, authenticate or like prove, prove legitimate ownership. Yeah, okay, all right, let's maybe say that I prove legitimate ownership, right, of the web server, or of the, yeah, I guess, server service. Right, and I guess also there can also be some like personal information as well. Let's say that, right, and maybe some, I don't know, yeah, personal information, right, about the owner, right, e.g., let's say email, email, phone number, possibly it could even be their name, it could be, I don't know, their physical address, etc. Alright, and again, I guess the idea of providing that is that if you provide this, well then if people have, I don't know, some query, of course they can contact you. And of course, yeah, if you actually provide all of this, then people are going to be more likely to trust you. Although, you know, people are not really going to provide their sort of real home phone number, right? That's going to be like a business phone number, business address. I think that should be fine for talking about the certificates, right? Then we probably want to talk about how asymmetric encryption is going to work. So let's say that, let's say the, alright, I guess we could talk about the digital signature some more as well. Let's maybe mention that, right? So since the digital signature, let's say since the digital signature is signed, alright, and the way this is going to work is it's going to be signed, so basically encrypted, right? Signed, encrypted, by the certificate authority's private key. Alright, so this is where a digital signature is different from, well, just, you know, encryption. Okay, so here they're going to sign it using their private key. And then basically what other people can do is other people can use the public key of the signer in order to verify that the person who signed it is basically the person who claims they signed it. because, for example, if someone doesn't have the corresponding private key, then when someone tries to when someone tries to verify or decrypt it, well, then because this person has a different public key, right, not the original, or sort of not the public key that matches the private key of the person who signed it, well, then it's not going to verify. Alright, so I think I'm probably going to draw a diagram to show that because it's kind of difficult to explain. Right, so since the digital signature is signed, by the certificate authorities, certificate authorities private key. Then I guess then it can only be verified. Can only be verified. By using the certificate authorities public key. Certificate authorities public key. Okay, so let's just try to draw this digital signature process. So what we're going to have right here is going to be the certificate authority. Again, they're going to have a public key and a private key. So what they're going to do, they're going to take some data. This could be, I don't know, some personal data from the person who owns the website. I don't know, it could be some random data. I'm sort of not really sure, to be honest. But basically they're going to take some data, right? They're then going to sign it. And really, when we say sign, I mean, it's just the same as encrypting. However, I guess really the kind of goal is different, right? That when we're encrypting, the goal is to basically make the data unreadable, or I guess kind of like ununderstandable, right, by the person who intercepts it. Whereas when we're signing, this is about proving the identity. And we'll see that basically it's using the opposite person's keys, right? So when we're encrypting, we're using the keys of the person we're sending to. Whereas when we're signing, it's the sender, it's the sender's keys that we're using. Alright, so what's going to happen? Okay, we're going to take the private key, we're then going to sign some data. Right, so when we do that, the private key, we sign the data, this then is going to equal the digital signature. Right, this digital signature can then be sent to the person who's requesting it. Let's say, this is us, right, the person who's visiting the website. What they would do, right, they would then take the certificate authority's public key, right, they would then use this public key basically to, decrypt or verify the digital signature. And the reason that works is because basically only the corresponding public and private key pair will actually work with the verification, verification process. If, for example, we use someone else's private key in order to sign it, then of course this public key is not actually going to be able to verify it. Now you might be thinking, like, let's say this public key, I don't know, this is like ABC123, right? That's the public key of this certificate authority. Now you might be thinking, let's say here, I don't know, we have some attacker. I can't really draw that. Let's go some attacker, and they could also send us a certificate, right? Claiming ABC123, and again they could also just copy, right, this digital certificate, and of course they could send us the same digital certificate. Now you might think in this case, it kind of appears like the attacker can sort of successfully pretend to be the server. However, the reason, the way this is prevented is that your web browser is going to have a list of trusted certificate authorities. So if, for example, they get some random IP address or some random certificate authority sending us this certificate, your web browser is not going to be trusted, because it's not going to be on the whitelist. Alright, and I guess if you want to look at that, they actually call it the root store. You can just go and Google Chrome, for example, right? You can look at the list of trusted certificate authorities. And your operating system is also going to have a list as well. Alright, so that's kind of the way they prevent random people from just sending you, digital certificates, pretending to be someone else. Alright, so hopefully that kind of makes sense, although it is a little complex, to be honest. Right, so that's kind of how they can verify their identity. Right, so I guess now then we probably just want to talk about the actual encryption process, because that's really what SSL is about. One, we want to verify their identity. Right, once we've verified the identity, then of course we want to encrypt the data so that no one can intercept. So that if someone does intercept it, they can understand it. Right, let's say once verified. Once the client has verified the server's yeah, I guess what, identity. Right, then the client. Right, the client will use the website's, yeah, I guess what, the website's public key. Yeah, public key contained within the digital certificate. Right, in order to encrypt messages. Right, encrypt messages and send them to the server. Right, yeah, okay, right, okay, let's say via asymmetric encryption. Right, okay, then let's talk about decrypting. Right, so I guess what, to decrypt, right, the server will use its, yeah, its private key. Yeah, I mean, I think that's fine, right? So to decrypt the server, we'll use its private key. Maybe what? Okay, all right, yeah. So let's maybe talk about the algorithm. Right, its private key, right, and the same, well, I guess yeah, the same encryption algorithm. Right, the same encryption algorithm, right, agreed upon with the client. Right, let's say in order to convert, right, and let's mention well ciphertext, plaintext. Right, so convert the ciphertext. Right, back into the original plaintext, right, that the user, or yeah, I guess, well, that the client sent. Yeah, I mean, alright, so probably here, you could like waffle on a bit more, but yeah, I think hopefully, that should get, well, at least maybe 5 or 6 marks, hopefully. Okay, so although we have actually finished all the questions, I think it is actually good to look at a practical example of this. So you can actually go here, I guess if you click this, right, you can then click on this connection secure, click on this one, right, this will show you the certificate. However, for some reason, I guess because I'm using this Kaspersky antivirus, this is actually kind of modifying the certificate for some reason. So instead, I've just used this sslchecker.com, and yeah, here we can see I've just done it on my own site. Now here we can see where it's got the expiration date, and actually, I guess, yeah, that's actually quite soon, right, that's coming up. Yeah, for some reason this is red, maybe I need to check that. That's not really important, right? But we can look at some of the key things then, like what's included in the digital certificate. So one is going to show you the website that it's issued for. So of course, well, this is the main website. However, I've also kind of approved it for these subdomains as well. Yeah, for example, sandbox, right? This is if you're using the add HTML custom function. Yeah, okay, then there's, right, okay, so you see here actually like organization, country, I've not included these details, although of course, yeah, maybe a more reputable company might actually include this. Right, so here then, right, this is actually the certificate authority. Now, Let's Encrypt, this is actually a free one. Yeah, there are actually a lot of paid certificate authorities, however, of course, I don't want to pay for the HTTPS certificate, so of course, yeah, I just use this free one. Yeah, and again, it's saying, well, obviously that's based here in the US. And then, for example, here, right, so I think this is going to be the stuff in the actual digital certificate. Yeah, okay, that's just saying, well, what algorithm is used for the signature, right, so SHA-256. And then, for example, right here, okay, this is actually the digital certificate. We can see what's inside. I mean, like serial number, I'm not really sure what that is, right? Again, it's got the algorithm. It's got things like the issuer, right? Obviously, when it's valid. So I guess, yeah, obviously when it starts, when it ends. Again, it's got the website it's valid for. Right, if we go down to the sort of more important stuff, well, here then, right, this is going to be the public key. And I guess we're saying the public key is 2048 bits. Right, and again, yeah, we can see, right, the agreed algorithm is going to be RSA. Right, RSA is a common encryption algorithm. If we go down, I think, yeah, I mean, this stuff is not really, I guess, well, it's quite niche, right, it's quite advanced. I guess I'm not really sure what that is, to be honest. Yeah, okay, so here then, if we go down, right, here is the actual signature. So this is the signature, and I think, yeah, this scroll is quite sensitive. Right, but I think if we go up, it should say probably that's from Let's Encrypt. Yeah, I can't see it on here, right? But basically this signature is probably going to be from Let's Encrypt. Right, that's the company that has actually signed it to sort of verify that I'm the owner of this website. Right, and again, yeah, that's going to be signed using Let's Encrypt's private key. Right, that can then be verified, I guess, using the public key, right, that they list here. Right, and again, if you just sort of go down through this, yeah, you can see where they've also got, yeah, I guess, well, here's the actual certificate contents. Yeah, this other stuff is really just like the metadata, I guess. Alright, anyway, so as always, hopefully this video is useful. It's a super long video. I think not quite as long as yesterday's, but yeah, still pretty long. Alright, and as always, if you've got any questions, ask in the comments, and I'll see you again in the next video.